Welcome to the lesson activities for section 2.4 for differential equations, Math 204. Consider the partially decoupled system. Find a formula for the particular solution to the system above with initial conditions x of 0 equals 1 and y of 0 equals 0. Okay, so we start with the part of the system that is decoupled, meaning it's a y prime and it only depends on y. It's decoupled from x. X does not influence that equation at all. So we solve dy dt equals 2y. You can solve by separation of variables. You will end up with y equals c e to the 2t. So that's one of my solutions. Like, I'm done there. I know the solution to the y prime equation. The general solution. If I want to know the particular solution that has this initial condition, I plug in 0 for t, set it equal to 0, and figure out what the c is. So y of 0 equals c e to the 0, which is supposed to be 0, which means c equals 0. So my y of t solution is 0 e to the 2t, which is just 0. Okay, then to solve the x prime equation, we have dx dt equals negative x plus 3 times y, and y is 0. So I'm really just solving dx dt equals negative x. You can solve by separation of variables, and you end up with x equals c e to the negative t. And then we use the other initial condition, x of 0 equals 1, to solve for c. So x of 0 equals c e to the 0 is 1, which means c is 1. So my x of t solution is going to be 1 e to the negative t, e to the negative t. Consider the partially decoupled system. Find a formula for the particular solution to the system above with initial conditions x of 0 is 0 and y of 0 is 1. Okay, so we start with the equation that is decoupled. So the dy dt equation, it has no x's in it, so I'm going to start there. Solve dy dt equals negative 3y using separation of variables, or perhaps you just know the solution because you've done this a bunch of times, that y equals c e to the negative 3t. Use the initial condition for y to solve for c. So y of 0 equals c e to the 0 is supposed to be 1, which means c is 1. So my solution for y of t is going to be e to the negative 3t, just replacing this c with a 1. Okay, and then we go to the dx dt equation and replace anywhere you see a y, we're going to replace it with this formula. So we have dx dt equals 2x minus 8 times y, which is e to the negative 3t squared. Okay, I'm going to simplify this a little bit. So I have dx dt equals 2x minus 8e to the negative 6t, right? When you raise a power to a power, you just multiply those exponents. All right, this is not as easy as the last one. So I'm going to have to solve this using lucky guess or integrating factor. I'm going to go with lucky guess, which says start by solving the associated homogeneous equation. That's supposed to be dx dt. dx dt equals 2x. We know the solution to this by doing separation of variables. We would get x homogeneous equals c e to the 2t. Step 2 is to guess a particular solution. This is the lucky guess part. So my y particular is likely to have the form of the forcing function. So it would be like alpha e to the negative 6t. Which means y, and that's an x particular, sorry. We're so used to using y as the dependent variable, but it's x in this case. So x particular prime would be negative 6 alpha e to the negative 6t. Then we plug into the differential equation, see if we can find an alpha that makes this work. Okay, so dx dt, that's negative 6 alpha e to the negative 6t equals 2x, 2 times x, which is alpha e to the negative 6t, minus 8 e to the negative 6t. Okay, so we get negative 6 alpha e to the negative 6t equals negative 6. No, there's no alpha on that. Okay. Equals 2 alpha e to the negative 6t minus 8 e to the negative 6t. Okay, so on the right, I'm going to factor out an e to the negative 6t. So I have 2 alpha minus 8 times e to the negative 6t equals negative 6 alpha e to the negative 6t. So now I can equate coefficients. I have an e to the negative 6t term on both sides. So this coefficient has to equal this coefficient, and we can solve for alpha. So negative 6 alpha equals 2 alpha minus 8. So negative 8 alpha equals minus 8. Alpha is 1. So that means my x particular is alpha e to the negative 6t, and I now know alpha is 1, so it's just e to the negative 6t. Okay, and then my x general is just the sum of x homogeneous and x particular. So x general would be x homogeneous, which is ce to the 2t plus x particular e to the negative 6t. And then I'm supposed to figure out the c value by using the initial condition we were given for x. So let me look up there. X of 0 is 0. So x of 0, that would be c times e to the 0 plus e to the 0 equals 0. So c plus 1 equals 0, so c is negative 1. So my x of t solution is this function, x general, but replace the c with a negative 1. So it's going to be negative e to the 2t plus e to the negative 6t. So the answer to this problem is both of these functions, x of t and y of t. So part B is to find equilibrium points of the system. So you find equilibrium points by setting dx dt and dy dt equal to 0. So let's see, I'm going to set 2x minus 8y squared equal to 0 and negative 3y equal to 0. And I have to solve these two equations with two unknowns simultaneously. So the one with just y's in it is pretty straightforward. We get y equals 0, right? So then I'm going to go over to the other equation. Now I know that y is 0. I'm going to substitute it in. And we end up with x equals 0. Okay, so the only equilibrium point is the point 0, 0.